Last time we talked about the atomic orbitals and how we can use quantum mechanics to describe the distribution of the electron around the nucleus. And we ended with the radial portion, looking at the radial distribution function for a hydrogen 1s type orbital. Now let's look at the angular portion, which depends on theta and phi, those angles from the z-axis and the x-axis. And the angular portion can be solved, for example, with one solution is this one here, which is for the pz orbital. And what this tells us is that as phi changes, goes from 0 to pi, then cosine phi will change as well. So we can plot that out. We can plot an angle here. Let's see. This is theta. Theta is the angle from z. So this is the z-axis. And then this would be the, we're plotting the y. And this tells us that as we go from, as we change the angle, we're going to go through 0 at 0, and then we're going to change sign as the angle goes negative. So this is what the angular part of the function looks like for the pz orbital. And you can see that if we square this, we get the figure 8 shape or dumbbell shape for what we're familiar with as a p orbital. And we should note that we saw that the sign of the function changes, and so this is taken into account usually in graphs or found in, say, your textbook by shading or color coding. So we have the positive portion of the wave function, the negative portion of the wave function, and this is the sign of the function here, not the charge of the electron. The electron stays negative, the nucleus stays positive, but the sign of the function changes as we pass through the nucleus. And so we see here we have a node, right, because the wave function goes to 0 right here, and this is a nodal plane. So with the angular portion of the wave function, we introduce nodal planes. With the radial portion of the function, we can also have nodes, but those would be, again, spherical shaped, because in terms of the radial part, it doesn't matter what angle, we're going to have the same result. Okay, so we're going to have two different types of nodes, and together these radial and angular portions of the wave function describe the electrons around the atom. Again, this is all for hydrogen-like atoms. We'll have to save discussing atoms that aren't like hydrogen for another day. But out of all of these Schrödinger equation calculated in these polar coordinates around the nucleus, we get 4 quantum numbers to describe each electron in the nucleus, or in an atom. And the 4 quantum numbers are, again, n, the principal quantum number that we saw from the Bohr model. And so this determines the energy that the electron will have, or the energy shell or energy level that we talk about. And n can have values, they're whole numbers, whole counting numbers. Okay, positive counting numbers. L is the symbol for the angular quantum number, and this we use to talk about the subshell, and it can have values that range from 0 on up to n minus 1. So depending on your principal quantum number, that's how many possible angular quantum numbers you could have. For example, if n is 1, then L has to be 0. When L is 0, we call that an s orbital, or s subshell. If L equals 1, that's the p orbital, or p subshell. Okay. M sub L is the magnetic quantum number, and it has values that range from negative L to positive L. So again, depending on what your n is, that gives options for L, which then gives options for M sub L. And so, for example, you could have if L equals 1, then that means you have M sub L possibilities of negative 1, 0, and positive 1, which means there's 3 different orbitals in the p subshell. Okay, and then the last quantum number is the spin, and this can only have values of positive 1/2 or negative 1/2. And again, these values are unrelated to these that came out of the Schrodinger equation. Spin helps explain the Pauli exclusion principle. Which says that electrons have to be spin paired. And spin is conceptually that the electron is like a sphere or a planet that is spinning on an axis. And that's detected magnetically, but of course we can't actually see the electron spinning on an axis. And in our next lecture, we will next 2 lectures we'll get to talking about the Pauli exclusion principle and how that applies in an atom. So thank you for your attention as we have explored the various possible shapes of atomic orbitals.